Hi everyone, today we're going to finish Unit 9 with topic 9.11, electrolysis and Faraday's law. So far we've been talking about voltaic cells, which are essentially spontaneous redox reactions that generate a voltage. Right, and so it's powered because of the fact that the redox reaction is spontaneous. It goes without any outside assistance. But electrolysis is what happens when you have an electrolytic cell, which is a non-spontaneous reaction. I should say redox reaction that requires outside voltage, otherwise known as another battery, basically, to occur. And basically, the use of electricity to create a chemical reaction is called electrolysis. Now, since it's a non-spontaneous reaction, what this basically means is that the cell potential, or E naught of the cell, is negative, or less than 0 is another way to say that. And so this basically works by forcing a current through the cell. So the cell potential itself is negative, and you force a current through it, and this is what forces the chemical reaction. Now current, which we call I, this is measured in amperes, and 1 ampere is equal to 1 coulomb per second. Typically, you can calculate current, which is I, by dividing Q, which is the charge, not the heat, but the charge, divided by time, which is in seconds. So the way one of these cells work, I'll kind of demonstrate, or at least draw a picture of it, is you essentially have one big tank. Actually, let me do this down here. You basically have one big tank. In this tank, you have your anode and your cathode. Both of them are together. And in general, it does not matter what the anode and cathode are. The reaction isn't actually dependent on that. These are connected by a wire, and over here you'll have a battery. Electrons, of course, will flow from the anode to the cathode, just like in a voltaic cell. But what'll be dissolved, or not even dissolved, but the liquid inside this is typically a molten salt. And so you'll have like molten NaCl, in other words, liquid NaCl, not dissolved, but NaCl that is a liquid. What'll happen here is we'll have Cl minus at the anode turning in to Cl2 gas. And this will generate bubbles, and those bubbles will leave the solution. At the cathode, you'll have the Na plus turning in to liquid sodium. And so you essentially have two reactions here. One of them, which is 2Cl minus liquid, makes Cl2 gas plus two electrons. This here is your oxidation, because the chlorine is losing electrons. At the same time, we have 2 Na plus, which is a liquid, and 2 electrons forming liquid sodium. And this is our reduction. And so if we want to calculate the reduction potential of the cell, it's always the same. E naught is equal to E naught of the cathode minus E naught of the anode. And again, you would get these numbers from a table. You don't actually have to calculate them yourself. This is just really for demonstration purposes. But E naught in this case will be the cathode, which at our cathode, we have the sodium reaction happening, which is negative 2.71, minus the anode, which is our Cl reaction, and that is 1.36. And the value that we get here is negative 4.07 volts. And what you can see is that E naught is negative, making this an electrolytic cell. Now, normally, when we have a voltaic cell, and I'll write this down here, in a voltaic, the larger reduction potential is at the cathode. So normally the cathode is always going to be the larger number, which is why it's positive. But in an electrolytic cell, the smaller reduction potential is at the cathode. So this is the exact opposite of what we've been talking about before. Because we're forcing the reaction to happen, this is going to make the E naught of the cell negative, and because of that, the smaller one is going to be at the cathode. Now, for any half reaction, the amount of substance that's reduced or oxidized in an electrolytic cell, specifically an electrolytic cell, is proportional to the number of electrons passed through the cell. And if we remember back to the Nernst equation, this is N, right? That value N. And so the amount of oxidation or reduction is directly proportional to the number of electrons, and we use Faraday's constant, F, to relate coulombs to moles of electrons. And because of this, we have Faraday's law, which I'll go over in the next slide, which can basically discuss how much of a particular metal is going to react as a result of that electron flow, which again relates to our current. And so you'll see in the next slide what I mean by this, but we can solve some interesting problems about how much metal is going to be reacted based on this flow of electrons. So in this problem, we're asked what mass of gold, which is AU, in grams, is plated by a 20-minute flow of 5.5 ampere current. So we have this reaction. Gold cations plus 3 electrons will make gold solid. Oftentimes what you'll do is you'll take some sort of a metal, like a cheap metal, like maybe zinc or nickel, and then you'd essentially cover it in gold, so you get a piece of jewelry that has gold but is not as expensive as a complete piece of gold. And so what we can do here is we can estimate the amount of gold that we can actually plate based on the current that we're going to drive through our electrolytic cell. And so again, this is for an electrolytic cell. This is why you might actually want to do this in real life, right? This reaction isn't going to happen on its own, so you force it with a current in order to get a nice piece of jewelry. Or sometimes you'll have, for example, pots and pans. You'll do this to get a really good pot or pan. So we're told that we have a 20-minute flow of 5.5 ampere current. As a reminder, current is measured in coulombs per second. And so the first thing we need to do here is convert minutes to seconds. So we have 20 minutes per minute. I have 60 seconds. And now my current here per second, I have 5.5 coulombs of electrons. Now we can use Faraday's constant F, which relates coulombs to moles. We have 96,485 coulombs per mole of electrons. Now in our reaction, I have 3 moles of electrons per 1 mole of gold. And then if I want to find the mass, right, at this point I'm at moles of gold. If I want to find the mass of gold, I just use the molar mass, or the atomic mass. So for every mole of gold, I have 196.96 grams of gold. Now we can go through. Minutes cancel with minutes, seconds cancel with seconds, coulombs cancel with coulombs, moles of electrons cancel with moles of electrons, moles of gold cancel with moles of gold. And finally, I'm left with 4.5 grams of gold. And so in a problem like this, we can see that if I make an electrolytic cell and I run a 5.5 amp current through it for about 20 minutes, I'm able to plate 4.5 grams of gold onto another piece of metal. So this is what they actually do in real life in order to get gold-coated jewelry, or maybe even like a steel-coated pan or something like that. We'll go through some more of these problems together in class, but for now, that's all. Thanks, guys.